This video is dedicated to the rest of chapter 14, and I will be continuing with the same example that was described in class. In that example, we had an independent variable, which was the number of TV ads, and we used the number of TV ads to predict the number of cars sold in a dealership. So we started by first generating the 6 numbers or 6 figures or 6 summary figures of correlation and simple linear regression, which, as you can see here, n represents the sample size, summation of x are those observations for the independent variable, and the summation of y, which represents the values of y, the dependent variable, and x times y, that's another figure that we're interested in and we're used in calculations, x squared, the summation of that, and summation of the summation of y squared, right? So these are usually used to calculate R, which is the correlation coefficient, but during class, we gone through the way to actually generate that using Corel, and we've gone through generating the regression analysis results, as you can see here in this picture. But in this video, I'm going to continue with the confidence interval. So the confidence interval has to do with the equation that we get from the results. The coefficients here represent B1 and B0. So B1 is the slope and B0 is the intercept. The intercept is that when we have, just to make sure we recall that, so for any regression line, intercept is the length from the origin, 0, 0, to when x equals 0. So that is going to be the intercept, while the coefficient of x is the slope, all right? And that is B1 in this case. But we have calculated them manually just to show you that we use these figures to calculate that manually. And the reason we do that is that we want to find the F statistic and F critical. F critical is not required. I mean, we don't really require those figures to calculate that, but to compare that to F statistic, we also get that from the statistics or the summary statistics that we get from the regression analysis. So this is just the manual way of doing it, and here you can see all the results that show the same numbers but within just a simple procedure, right? So now that we have this equation, so to say, we have this as, well, y hat, that represents the projection or the prediction. It will generate always a value. So depending on the number of TV ads, we will have various numbers of cars sold, right? So there is a confidence interval for that. And when we say that there's a confidence interval, that the accuracy of that equation is going to be something like, if we want to cover 95% of that, is going to be between two values. So that what represents the confidence interval. So when we say, well, we want a confidence interval for this regression equation, we mean that, well, how much accurate it actually covers, all right? So that whenever we have this applies to a whole range. So this applies to the equation itself. Then we have another type that is called the prediction interval. So that's an interval that applies to a specific or an individual prediction, all right? So that has to do with a specific prediction. Let's cover the first one. And as you can see here, this is according to the book. The formula is, as you can see here, quite complex. So it equals the result from that equation. So if we have, for instance, if we want to find the confidence interval for x equals 5, as it is in this case, that would be the y hat of that. So we're going to plug in 5 here and find the answer from there and plug in it here. And then t critical, that's exactly the t critical that we have here, all right? And then SE, so that's the standard error. And that we capture from the summary of statistics, as you can see here. So that's the standard error here, SE, right? Which we don't need to calculate that, it's already there, so we just capture it straight away from the summary output. And then we have the standard, the square root of 1 divided by n, and that's the sample size, so we do have that. And all these numbers, all these figures are those six summary figures of correlation and simple linear regression. So it's going to be, for instance, here, x minus x bar square, and x bar is going to be the average, so we can calculate that from the average here. And x would be, in this case, 5. That's the value that we're interested in. And then it's going to be the summation of x square, which is this value here. And, well, the summation of x squared, so we take this value here and we square that, divided by the sample size. It's a quite complex formula, but I have it here for you, just basically to trace and see what the referenced cells and where each value came from, all right? So what I did basically was that I applied that step by step and made sure that I got the right answer. So that was it for the confidence interval. Now, if the prediction interval is required, then we're interested in a specific value. This range applies this applies to the whole range of values that are generated using this formula. But now, for a specific value, we have also a prediction interval. So let's move to that part. There it is. So here, just to conclude the confidence interval part, the way you can interpret the confidence interval that we just generated is that we are 95% confident that the average number of cars sold for all weeks in which 5 TV ads are used will be between 19.15 and 28.75. Okay? This is how you can interpret that. Now, the prediction interval, as you can see here in the previous example, the confidence interval is for the average number of cars sold for all weeks. So this is for the average, and that's why we have average here. So we're measuring the distance to the average. But for the prediction interval, we're measuring, let's see where that, there it is. So here, the difference is that we're interested in an individual. So the distance to that individual week. So if it's 5 in this case, it's going to be a different number. And usually this number is going to be, or the interval is going to be wider. So it has a more marginal error in this case. All right. So what we have here, as you can see, plus or minus, plus for the upper confidence level limit, and minus is for the lower confidence limit. And there, again, this is exactly the same. The only difference here is that we have 1 plus to 1 divided by n. So everything else is the same as the confidence interval formula, except for that addition. So this is the only addition that we have here. So again, what you can see here in this sheet that you have access to is that we have this equation, and all the values are referenced, so they can actually trace where each value came from, and that applies to the lower and upper confidence levels or limits. All right. So this is it. This is it for calculating the upper and lower confidence limit for the prediction interval and for the confidence interval. All right. Now let's move to testing the significance. This is the last thing that we have here. We need to test the significance of the slope. So we have the slope here. The slope is the number of TV ads. So the number of TV ads in this case can explain around 70% of the variations in the number of cars sold according to the results here. But how much is this significant? This is what we have. This is where we add the hypothesis statement to just see how significant this coefficient is. All right, and we use beta because, like, B is the small letter for that, but the capital letter is beta. So beta 1, B1, and that is turned into beta 1, and that's supposed to be the population parameter. So we're testing if the population parameter is significantly different from this or not. Okay, this is how we measure it. If the population slope is 0, then X does not affect Y. Okay, so if this turns out to be significantly 0, and we would conclude that there is no relationship between the dependent and independent variables. So this is an important test that we have to look into before we proceed. And guess what? You don't need to do this. You have the values already here. I'm going to show you how, but let's start with how the hypothesis statement looks like. So the null hypothesis would be like beta 1 is 0. So unless there evidence that we have, there's a significance, we assume that it equals 0. So the original assumption is that there is no relationship. There is no relationship between the number of TV ads and the number of cars sold. Unless the value that we get for the p-value and all other indicators of rejecting the null hypothesis exist, we assume that there is no relationship here, right? And the calculations are similar. We don't need to go through that. You have this line, and this line sums up pretty much everything here. So the t-statistics is 3, and we don't have the t-critical. If you remember, we had that in previous analyses for ANOVA, for instance, and that's ANOVA, by the way, so we are still there. But what we can look at here is the p-value. So we have the alpha here is 5%, and the p-value is less than that. So this makes us reject the null hypothesis. Another indicator is the confidence interval. So we don't have 0 here. So this should be either like 2 minuses or 2 pluses, as we can see here. Like we have 2 positive values. So between the lower and the upper confidence limit, there is no 0. So 0 is not probable within the 95% of confidence interval, which makes us reject the null hypothesis that beta 1 equals 0. All right. So this supports the relationship between the number of TV ads and the number of cars sold. All right. So I added the manual calculation here just for you to see how the upper confidence limit and lower confidence limits are manually calculated, right? And these are the same numbers that we have here, right? So this is just to say that we can calculate it manually. This is the formula for that. But anyways, this table, the ANOVA table here, shows us pretty much what we need. So the only thing that you have to calculate manually on top of that is the confidence interval and the prediction interval for the regression equation. The assumptions for regression analysis. So there are some indicators that we have to look and test to make sure that the results that we get from our analysis can be trusted and are reliable, right? I'm going to go through some assumptions that we have to test and we have to see and evaluate and revise or review to make sure that the results that we're getting from the regression analysis are reliable. Assumption number 1, the relationship between the independent and dependent variables is linear. So when you look at the values, as you can see here in our Excel, you have to see some sort of linearity, as you can see here. This is as opposed to other examples where you can see, well, this is not really linear, it's pretty much polynomial. So there's a curve here. It's not really, you can't measure that in any other way than actually just visualizing the scatter plot and see if there is some sort of linearity that you can capture at. So this is a review that you do using your eyes, basically, right? Assumption number 2 is the residuals that exhibit no patterns across values in the independent variable. I'm going to explain this and how you can actually generate this plot. You have to generate the regression analysis results again, but now, so we go again to data. I can't see that in this picture, but if you follow the same procedures, data analysis, and then you're going to get this. Moving to regression, and then we're going to do this again. Number of cars sold for Y, and X is going to be number of TV ads again. And then here, we're going to check the residual plots, right? And let's put that in a new sheet. We have to check the labels, and we click OK. So what is this residual plot? What does it mean? So remember the line, the regression line. So the regression line is put as the origin here, so it represents now the axis here. So if you take it, it's usually a linear line, like it's going up or it's going downward. So take that line and make it a horizontal line like this, and adjust the plots, those points accordingly. These points should feature independency. What does that mean and how can that be featured? In our case here, they have to be like randomly around this axis so that we don't have too many points in one side. Now, this is as you can see here. So you're taking this line and you're putting that as the horizontal line, and around that, all the points should feature some sort of, as you can see here, no pattern in this residual plot. This is as opposed to this one. You can see here that there's some observations here, but then we don't have any observation. And then back to that lower part. So we see that there's some sort of pattern, and this one of the violators for the results. So we don't really trust the results that we get if we see this pattern. Then assumption number 3 here, the residuals, if we come back to this, they're going to look like this, and that's going to be one of the violations for the results that we get from a regression analysis. So this is an indicator that raises a flag, and we shouldn't really take the results of regression analysis seriously if we see it. It has to look uniformly like this, right? If the number of the variation between numbers increases, there seems to be some sort of correlation between variables. I'm not going to talk into the details of that, but in general, the pattern that, if there's any sort of pattern that does not reflect randomness, this is a red flag. Assumption number 4, the residuals from the ordered pairs follow the normal distribution. So what you see here, this should represent a normal distribution. Okay, so it's a random variable with a normal probability distribution. This was it. We have another example that I'm not going to cover here, but you're going to have access to it. It just represents another example with a negative correlation. So instead of having a line that goes upward, it's going to be a line that goes downward. So I recommend that you go over that example just to see how the numbers would look like. In this example, for instance, that we have the impact of your speed, the mile per hour, on the MPG, mile per gallon. So the gas consumption, if it's correlated with the speed, and you have some sort of data set to test that and to see, also check all the other patterns. You're going to follow exactly the same procedures to test the hypothesis, different types of hypotheses for the regression, for the slope, and for intercept. And you're going to probably also try to generate a confidence interval, a prediction interval, and etc. So take your time with this. I have that also here, so that you have access to that as well. I have it here as part of the 2 examples. So one example represents the positive relationship example, as you can see here, and the other one is the negative relationship example. I hope this video explained a little bit the rest of this chapter, and let me know if you have any questions.